Our first talk today will be a workshop on end-to-end generative AI workflows built for developers. We have two speakers, Adam Tetelman, Principal Engineering Architect at NVIDIA, and Bartlomiej, who is an AI field engineer at Canonical. Adam Tetelman is a Principal Architect at NVIDIA, leading cloud-native initiatives across the company. He has been in cloud, DevOps, and AI-related work over the past 15 years. And he built out NVIDIA's Deep Learning Institute, as well as engaged with numerous MLOps communities throughout the course of his career. Bartlomiej is a solution architect leading AI field engineering initiatives within Canonical. He builds tailor-made data ops and MLOps solutions for the pharmaceutical industry, financial service, and public sector, among others. The floor is yours. Take it away, Adam and Bart.
Thanks for joining us today, everyone. Today, we're going to talk about end-to-end generative AI workflows. So I think a lot of us at this conference are probably familiar with the POCs that we might build to get an AI agent up and running. But today I really want to focus on what it makes it production ready. So how can we add real business value and not just build a toy that's sort of fun and a cool demo? So today, going to start off just level setting, talk about the components that go into that POC that might run on a workstation. Then we're going to talk about how to take that POC and make it into an MVP that meets a real business use case. And then how we might want to take that MVP and make it more trustworthy, more explainable, so that when we put it in production, it's going to be robust. And then once it's in production, what really means it's production ready. So what is everything that happens for scalability, for security, for compliance, and behind the scenes. So we're going to go through all of that, and then we're going to talk about some more advanced use cases you might do and use a case study to show how the tools that we're using can solve all of these requirements. And then we're not just going to talk about the case study, but we're going to do a demo. So first off, what are the fundamental building blocks here? So you've got an inference server, and you've got a foundational model. So this is going to run usually on Kubernetes, but if you're at this level, you may only just be running this on Docker and Docker Compose. And this is going to give you a chat API where you send in text input and you get text output. So it's like a toy. It makes for a cool demo, but you wouldn't put this in production. And so to take this to production, you're going to need to add a few more components. So rather than just running it on a Docker container or running it on Kubernetes, you're going to want a platform that's specifically built for inference. And so this inference platform will handle things like storage mounts, model movement, deploying the actual container. So it's not just a Docker run command, but a CI/CD YAML file that's going up and going down in this version controlled. And then you're also going to want to introduce more than just an LLM API. You're going to want a conversational chatbot API, something that handles conversation history, something that handles multiple sessions, some sort of AI agent. So it's not just doing one thing, but it can continuously have a conversation, maybe has access to AI tools that do things like running code, doing math, maybe even doing search. So this gets you to the point where your system can actually add real business value. These are the things you would want to do, but it's not quite ready yet. So this is where RAG comes in. So I think a lot of us have heard of RAG, and if you haven't, or if you don't know what RAG stands for, it's Retrieval Augmented Generation. And all of this means is that the context of the LLM is going to be fed with some additional context from a database. And so when I go and I ask my agent a question, instead of just using the knowledge that's baked into that model, it's going to go out to the RAG system. It's going to use a different type of model called an embedding model to find content that is similar semantically to the question I'm asking. And then it's going to take maybe a PDF or maybe an image or maybe a blog post that is similar to my question. And it's going to inject that knowledge as context into the LLM. And then when the LLM is spitting out a response, it's going to have all of that extra knowledge to pull from. And so this is really good if you have a lot of new information coming in that you need to feed into your LLM. Say you want comments or new product documentation or blogs, and you want that to always be in your chatbot. but you don't want to constantly be training a new foundational model every few weeks, because that's very, very expensive and it's very tricky. So this is where RAG is going to help. It's going to get you that data more up to date. And it's also going to make it more trustworthy, because when you get that response, it will cite the exact data that's coming from. So you get explainability. And this is really important if we're doing something that's more than a toy and we're actually putting in front of customers, or we're using it to drive our business. We're going to need to know that the data we're telling them is sourced somewhere. And then you're also going to want to pull from external data, maybe from the cloud, maybe locally. So this is all good. But it still doesn't make the model performant enough. That there are a lot of cases where just having the data maybe isn't good enough, or you may have many, many similar documents so that the RAG just doesn't do what it needs. And so this is where we add fine tuning. And this is going to not just explainability, just overall quality of your model will improve. So we're not actually training brand new foundational models in this fine tuning pipeline, but what we're doing is something called PEFT, or parameter efficient fine tuning. You probably heard of LoRA, which is a low rank adaptive learning. The basic thing here is, instead of training the entire model that you see in this diagram, we're training a small layer that sits on top of the model. And this is a lot faster. So you're not talking months with hundreds of GPUs. You're talking about hours or days, depending on your data set. But this is going to let you take that foundational model and inject the specialized business knowledge or the specialized industry knowledge into it. And this results in the quality of results just looking better. The performance of your system looks better. And you're going to have less queries and less RAG lookups, because the knowledge will be baked directly into your model. And so that gets you a system that works and will be great, but it's not production ready yet. I wouldn't tell anyone to put this into production, because there's a few things that you need to do before you get there. And this small changes on this slide, but what I've done here is shown that you're going to need to configure your system to do scaling. So you're not just going to want to deploy one inference server. You're going to want to deploy N inference servers, and you're going to want that to go up and down over time based off of a lot of different parameters. Similarly with LoRA, you're usually not just going to deploy one LoRA. You're going to want to deploy many, and depending on if you're doing different types of customers or different quality, you're going to need some system that can maybe manage that. And then safety is a big one. So between this slide and the last slide, I introduced some sort of guardrails. And basically, what's really important when you go into production is that the AI system is not given full autonomy. And so you need some system in between all of the inputs and the outputs to make sure there's no PII being exposed. Things are on topic, things are not toxic. That, if the chatbot is saying things that are completely inappropriate, instead of sending that response, you send a sort of pre-programmed response that prevents abuse. And so if you have all of these things, I would say you have a system that is ready for production, ready to scale, and is robust enough to really start adding real business value. But that's not it. So there's all of those components, and there's all of those different system pieces, but there's a lot that needs to happen behind the scenes. So first off, like with any software system, you need to take care of security. Security is really important. So models, make sure those are scanned, but all of the containers, all of the software, all of the microservices need to be scanned regularly for CVEs. Make sure that a lot of these new open source things that are coming out for LLMs every few weeks, sometimes if it's only been around for a few weeks, it's not robust. So we need to make sure we're scanning these things. But something that's a little bit new with LLMs is compliance. So wherever you're getting your model or your data to train new models, you're going to want to make sure those are going through regular compliance audits, and that if, say a data was found in a data set that wasn't supposed to be there, that's breaking some legal agreement or some SLA, that it's removed immediately and a new model is deployed that is not out of compliance. So that has to happen to really be a production system, and also standard lifecycle. So A/B comparisons, rolling upgrades, things like that, really important. A little difficult to do with some of the LLM use cases. So it's easy to do a blue-green upgrade if you're using a few VMs, but if a single model is using 8 or 16 GPUs, the way you do a rolling upgrade can be more difficult. So you're going to want to make sure that the toolchain you're using, the platform, can handle resource-constrained environments and knows how to handle something like a GPU appropriately when doing rolling upgrades. Similarly, you're going to want to make sure that the toolchain you have is not static, is not set at one point in time, because just in the past month, in the past 3 months, we get new types of fine-tuning. We get multi-node inferences now becoming very relevant. There are performance improvements that come with models all of the time. There are new models that come out all of the time. And so it's really important that the tool chain you use can be flexible and adapt and pick up these new capabilities, while also running the workloads that are deployed and being backwards compatible, because you don't want to always need to be on the bleeding edge, but you don't want to be stuck 6 months or 12 months behind when things are moving so fast. And a big part of that is support. So when you're going into production with all of these LLM systems, it's a very large stack. So we're talking about everything down from the hardware up to the API endpoint, and then the application software, the platform software, the infrastructure software, everywhere in between. And most of that isn't going to be your code. So if you're running a foundational business application off of someone else's code or someone else's platform, you're going to want to make sure that it's supported. And so if you just pick up a open source project off the internet, that's great, but make sure that the open source project has a rich community. And if you can get someone to support it, so when something breaks, you can get patches and bug fixes. You have a 24/7 number to call so that your business critical application is not reliant on some random GitHub. That's critically important. And so with that, I want to talk a little bit more about some of these advanced workflows and then start discussing how we've done that in the demo we're going to show, and some of the solutions that our companies have put forth for this. So I described sort of a production-ready LLM chatbot application, but there are a lot of ways you could take that and grow it and expand beyond that sort of basic use case. So things like dynamically scaling up and down the resources in the cluster, or the different inference services in the cluster based off of the utilization, based off of budget, scaling all the way down to 0 so that you're not wasting resources, up to n, depending on how bursty you need to be. You may need to do this scaling up multiple models, multiple different types of models, maybe multiple different families of models, maybe with a system that has an agent that is able to swap customers between these different models to do A/B comparisons. And so while you're doing this, you're probably going to want to collect data, different inference paths, different models, be able to assess that data, and maybe even then use that data to, on the fly, create new LoRA adapters and do fine tuning, evaluate those in the pipeline, and then deploy them back into production, all without taking anything down. And, I mentioned a lot of components that you would need. So on this slide, we have sort of a simplified version of those components that all of the use cases, all of the requirements I've discussed can be accomplished with a stack. So we've got, on the NVIDIA side, we've got the NeMo suite, which handles fine tuning and LLM. So in this case, guardrails, microservice that stands in between every input and output. We've got Customizer, set of microservices that can create the LoRA adapters and do all of the fine tuning and evaluation. And then we have NVIDIA NIM, which is the premier way to do inference and do it in an easy way that's enterprise ready and also very performant. And I'll talk a little bit more about that in a few slides.
Yeah, and maybe let me add it to this. So I love the capabilities which were just shown. And I know that this is what data scientists are looking for, and this is what data scientists are using currently. But we also need to think about all the people who are the platform engineers who are providing the platforms to enable these capabilities on top of it. We are talking in context of RAG. We are talking about providing the vector database. We use for our demo OpenSearch, which is providing us really, really great capabilities in the area of not only searching for the using the similarity search, but if you have a lot of logs, you can also ingest them and search them through this and to extract the information you need. Because not only the vector databases are great to add to the context, what we usually call RAG, it's not only vector databases, there are multiple sources of information that you put into the context. And this is amazing to have a plethora of tools in open source world. So OpenSearch is one of them. To host efficiently NVIDIA NIMs, NVIDIA NIMs comes with the integration with KServe. KServe is the inference engine which allows you to host NVIDIA NIMs in the environment. It is helping you to expose the metrics that the models are exposing. And then also it's allowing you to do the post-processing on them thanks to the integration with Knative. So the functional paradigm that is in the case cluster, it's allowing you to use read resources for the post-processing of the requests in case you would like to do the data drift detection or model drift detection in this. And all of it, usually you want to have something that will help you with orchestration of the whole process of MLOps. MLOps process requires multiple steps, including training, fine-tuning, verification, validation, pre-processing of the data. Kubeflow is an umbrella project which is coming with the Kubeflow pipelines, which allowing you to build this kind of pipelines and processing and workloads that will repeatably retrain your model or deploy your model. And all of this needs to be observed. The code that you see on the slide currently is a shortcut for Canonical observability stack. So this is a stack to monitor this stack. We built our stack on top of Kubernetes cluster with NVIDIA operator and with networking operator, which allows us to efficiently train models, but also to efficiently run all GPU accelerated workloads. And if we go deeper into the production grade infrastructure that is there, so we can go into having what is underneath the Kubernetes cluster. It can be any Kubernetes cluster, but how can you deploy all the things on any Kubernetes cluster? We are using a tool called Juju, which allows us to deploy our AI tools, MLOps tools, data fabric tools on top of any CNCF compliant Kubernetes and most of the public and private clouds. So this flexibility is giving you the ability to deploy RAG, but next day, if you need a new open source tool which is added to the suite, you can add it there. And Adam said about selecting the open source tooling and have someone to do the enterprise grade support on this. We launched the Ubuntu Pro subscription where you can get exactly this support for your open source tooling that you are using in production grade systems. Next.
Yeah, and I think the thing you mentioned just there about flexibility is really important. All of this is moving so fast, so having flexibility down at the hardware layer, at the platform layer, new data sources, like you mentioned, it's going to be totally required in probably 3 months to support new models, new data types, new fine-tuning methods. So flexibility up and down the stack is it's a table stakes for this stuff. And so talking a little bit about the application layer that NVIDIA is providing in this demo is NIM. That first thing is flexibility for model support. So when you're going to deploy, you're going to want not just one family of models, but you're going to need support for all families of models. You're going to want A/B do comparisons for the things you're building internally and the things that are available open source. And when you're doing that, you're going to need the features I talked about, multi-node inference and PEFT, but you're also going to want to make sure that all of your microservices are interoperable, maybe within an ecosystem like NeMo, maybe outside of that ecosystem, supporting whatever's coming from TensorFlow or PyTorch or other open source projects. You're going to want to be able to switch modules in so that you can just take the best parts of a supported stack. And then, you mentioned the standard metrics and open telemetry and different cloud native stuff, which is super important, but also important that can be deployed anywhere, right? So this is another thing that we've worked really hard with NIM to do, deployment in every CSP, deployment on-prem in any Kubernetes stack, deployment in air-gapped environments. And so if you are in the cloud, if you are on-prem, if you're hybrid, you're not going to want a different software stack for each one of those environments. You're going to need your software stack to run everywhere you run. And that's very true with LLMs, especially when there's going to be different hardware availability in different clusters. So this sort of ease of deployment, deploy everywhere, and enterprise-ready are table stake functionalities of NIM. The real differentiator from what I've seen is performance. I think you'll see this in the demo. But what we do with the models in NIM is we take open source models, we work with the creators of those open source models, and we optimize them, we hyper optimize them for the runtimes that they're deployed in. And so when you run a NIM on a CSP or on-prem, it's going to detect that GPU, and it's going to run a model that has been specifically optimized for that runtime environment, and it's going to give you the best possible performance. Lastly, just a little bit about the fine-tuning aspect. So we're not going to show fine-tuning in this demo because that would take a little bit too long, but we will show the LoRA adapter that we created with fine-tuning. And so to walk you through a little bit of what that looked like to create that adapter, we had a data set in a database. We took that data set using the NeMo Data Curator, which is an open source project right now. We created a high-quality data set out of that. We then took that high quality data set, we threw it in a data store that manages multiple models, multiple LoRA adapters, multiple data sets, and that was the NeMo data store. We then use that data and those foundational models to create a fine-tuned LoRA adapter with the customizer, which is the highly optimized for fine-tuning. It does a lot of special things to parallelize the effort, so it's very fast and based off of the NeMo framework container that's open source on GitHub. And then we ran that through evaluation. And so we looked at performance of that model. We looked at the accuracy against industry benchmarks, and then we looked at accuracy against our proprietary data set. And so after we did that, we deployed it into the NVIDIA NIM, and it ran. And so I think we're going to hear more about this demo now.
Yes, sure. So during the demo, we will be showing you the platform that we built and the use case that we implemented. From the moment you put your data into the object storage, so you prepare it, it can be in the form of text files, markdown format, in terms of PDFs, applications, Excel sheets. All of them are supported. It's going to ingest the data, create embeddings using the KServe embedding, and then save all of them into the OpenSearch. This is going to be done using the kubeflow pipeline, so the repeatable circle of ongoing pipelines which are generating the output. Later on, we will also use the KServe with the Llama 3 deployed on top of it. And we will be connecting to all of this using the Streamlit UI application, which is allowing you to ask questions and see what is the context and what is the answer from the model. Let's see it in practice. Okay, so looking at the demo, the demo is deployed on top of AWS, and this allows you to. We are using the Juju to deploy on top of it, on top of any public cloud. So we are starting with what we have inside of the demo. We have Kubernetes cluster. We have monitoring stack, which we called COS. We have also the OpenSearch and Kubeflow deployed. So if you look into each of them, you will find that our Kubernetes cluster is, in fact, having 3 CPU-based nodes and 2 GPU nodes. We are using A10G in AWS. So they are not the most powerful ones, but even with them, we are able to generate over 30 tokens per second during our inference. So for me personally, it was really interesting to see how fast it's working. Also, all of it is attached to our observability stack. So as you see on the top, there is the COS section. The COS is allowing you to monitor all of the stack. And this will be the ongoing theme whenever we go through the rest of the solution. The canonical observability stack consists of Prometheus, Grafana, Loki, and Alert Manager. Of course, Prometheus is used for metrics, Grafana for dashboards, and the Alert Manager is really important here because for production-grade systems, you want to be alerted every time there is the event that you don't want to be here, error, a failure of the node. So this is allowing you to connect to the tools like PagerDuty, which allows your ops team to be actively changing things as soon as they know that there is the issue within the system. So these are the tools deployed within. We also deployed OpenSearch. I deployed OpenSearch with only two nodes, but we can easily scale it out. One of the key things that when I'm talking with our customers they are talking about is how hard is this to deploy the suite of tooling. Kubeflow consists of over 20 applications, and as you can see here, they are all being deployed and maintained using the single command. So this is making the day-to operation way more easy and manageable for even the small teams of operators. If we go now to the Kubeflow, inside of the Kubeflow, you have few main parts that we will be talking about today. One of them is Jupyter notebooks, so Kubeflow notebooks that are there. It's allowing us to create the flexible environment for our data scientists, and we can use as a base for them NGC containers, which comes with a lot of already pre-installed libraries. If you prefer to use, if you don't have the GPUs in your environment, you can also use the predefined notebooks which are already there. In this case, when you will be going through the GitHub repo of the demo, please check that inside of the repository, there is the folder called documents. If you want to try to use your documents, drop them in text format, markdown format, wherever you want, and then run the notebook. It's all in the README file that you will be seeing in the repository, which will create the bucket for you, it's a place to store it and upload it into this, all of the elements to this from this folder. If you go, then what you need to then do is to run your ingress pipeline. Ingress pipeline will set up your OpenSearch index. It's going also to download the data from object storage, remove unsupported format for you. It will not fail, but remove them. And then using embeddings, ingest them into OpenSearch so that later on you will be able to use them within the with the Llama as a context to it.
So if you go into the what's happening underneath the hood of it, so what was deployed in the environment, you will see that you can see that this is the ingestion pipeline that is going in, and you have a Llama 3 being deployed here. So what it means is that you already have a model inside, so you can use it. So what you need to do to deploy it, to have a name, first of all, you need to enable connection to the Docker images that are part of NIM. Second thing is, it's recommended by me, is to use the PVCs for the caching. These models are really huge. They have hundreds of gigabytes even. You don't want to, at each scaling of your model, to recreate, so to download it again. Later on, what else is really important is that you need to have a cluster serving runtime and the model which are aligned with each other. the thing that I really like about the documentation that was provided with it was the support matrix. You are getting which GPU you should use, how many you need to optimize for the certain profile. So this gives you the ability to run it efficiently on the scale that you need for your use case. And if you now go into the and now let's go to the NIMs. So I created this application. This is a small application with the Streamlit. And each time you ask the question, the chatbot will reply in which context it was used with, what was the answer, and what was the part of the context you used. So every time you see what's happening with it, from perspective of the user, is giving them the certainty that based on these documents, I replied like this. And with this, I would like to finish our presentation and would like to thank you all for joining us today. And if whenever you have questions about NIMs, Kubeflow, or running the AI workloads at scale, feel free to reach out to both me and Adam. Thank you.